Hey class. This in this video we are going to take a look at one of our last topics, heat transfer. Um, and there are three major elements to heat transfer. The first being conduction, then we'll look at convection, and then radiation. Okay. And so for each of these, I kind of have I kind of have a keyword. So for conduction, the keyword here is through. Okay, this is when heat moves through an object. Okay, easiest way to kind of think about this is imagine you have, I don't know, there's some wood and you've got your campfire with the wood, and if you take a metal rod and stick it in the fire, right, the heat is going to move through the rod to your hand. Okay, but it's moving through the rod. Okay, that's conduction. Um, when heat moves through an object to get from one place to another. Um, and, you know, if we're looking at this on the molecular level, right? So if I zoom in, here, let me switch. If I zoom in on the rod here, right, you've got all of the atoms of the metal. And essentially what's happening is these ones start vibrating a lot, which hits these ones and they start to vibrate and they start to vibrate, right? And those vibrations are passed up the rod, right? As it moves through the rod to get to your hand. But that's what conduction is, right? Conduction is any time that heat passes through an object to get from one place to another, okay? So really simple way to kind of think about and look at convection. Easiest way to block or conduction, easiest way to block conduction is to remove the contact, right? If my heat is all stored in object A, and if I don't want it to get to object B, then I just need to separate those objects, right? Now there may be something in between, right? The two objects that the heat can conduct through to get, right? This could be air, it might be wood, it might be plastic, right? But depending on what I have in between A and B, right, that's going to change how well heat can conduct through this gap. If I was being really crazy, right, I could try to make a gap. I could put a little thing in here and I could suck all the air out so that there was nothing there, right? If this is a vacuum, right, meaning that it's void, there's nothing in that space. Then heat can't conduct, right? There's nothing for it to pass through if that's a true vacuum. If there's air in here, then it can conduct through the air, although air doesn't have a great thermal conductivity rating. So that's what conduction is. It's when heat is moving through an object, okay? All right, let's look at convection. So what convection is, and if you took the geology class, you've seen this a whole bunch, and right, we've seen convection a lot, okay? So my word for convection is when heat moves with a material, okay? So for example, let's say that, you know, you've got the fire of your stove and you've got your pot in the fire. Okay, hold on, let me say fire and pot above the heat. Okay, and then let's say you've got a bunch of water in here. Okay, so what convection is the water here at the bottom is going to heat long before the water at the top heats. Okay, and so as this water at the bottom gets hot, when things heat, they expand. Okay, so imagine, right, this block is this size. Well, let's say it expands just a teeny tiny bit because you heated it, right? I mean, I probably exaggerated that expansion, but now this piece of water is less dense than the water above it, and so it's going to rise, right? And since it's hot, right, it's carrying this expanded warmer water is carrying that heat with it up to the top, right? Then it gets up here, uh, and it doesn't just leave a gap, right? It doesn't expand up and now all of a sudden there's a hole here, right? The water from the top is going to sink into its place, right? And so if you look at this, you can see there's a cycle. So as the water heats and expands, it rises to the top. When it gets to the top, it's going to lose that heat, right? It's going to dump that heat out into the environment in different ways, right? It may conduct some heat into the air. Some of the water may evaporate, right? And if that happens, right, if the water evaporates, it'll carry the heat with it. That's more convection. Uh, or it may, and we'll talk about this, it may radiate some of that heat. We'll talk about what radiation is in a second. But anyways, it's going to dump some of its heat to the environment up here and cool back down. When it cools down, its volume will decrease again, becoming more dense, allowing it to sink, right? And you get this cycle, right? Convection is all about cycles, where you have a heat source that's on the bottom, it's heating an object, the heated stuff rises to the top because it's less dense, right? This is driven by density. But the reason why the heat moves, right, because we're talking about the heat transfer, the heat is moving with the material, right? That water that's now expanded and hot carries the heat with it to the top. And then it dumps the heat off. I probably should do that in red. Dumps the heat off, and then once it's cooled, it then sinks back down to the bottom for the process to happen all over again, right? That's what convection is all about, and hopefully in the simulations that I posted with the lab, you were able to kind of see that and notice those patterns, especially in that second one. Towards the end, you really, I think, could easily see the cycles of the rising material and the sinking material, right? But the key word here for convection is that we're moving with, right? Just a quick practical application of this that we've seen, right? When you look at the Earth, right? You have the core of the Earth that is really hot, and surrounding the core, you've got the mantle, and then, and these aren't all of the layers, but then you have the outer part of the Earth here. But anyways, right, you've got convection currents happening inside the Earth, right? Because if the center of the Earth, and my Earth is really off center here, but since this is much hotter, right, this material here that's close to the hot core is going to convect up, and it'll cool up here, and then it'll move back down. But you have these convection currents up and down here, and that pushes on the plates, right? And we learned, right? And so these plates up here are getting pushed on, and so that causes all the tectonic movement that we see in geology, right? But it's convection that's driving it, and the heat is moving with the material. Okay, that's the key word, okay? Conduction is through, convection is with. And so the last one, radiation, this is when heat moves as light, okay? It's as simple as that. Anytime that heat energy is transferred in the form of light, typically we talk about this in terms of infrared radiation. And in the videos in the labs, you saw some IR cameras, and you got to see a bunch of different examples of this. Right, the easiest way to explain this is think about space, right? So here's the Earth. Put some water on it too. Ooh. Put some water on our Earth. And right, the sun's way over here, okay? And between the Earth and the sun, what's in there? Okay, well, you have, Mercury and Venus in there somewhere. But aside from those two things and a couple of rocks, right, it's a void, it's a vacuum. I think there's two M's. Vacuum, I don't know. Maybe I don't know whether, there's two of something in there. Maybe it's two U's. Two U's? Nah, I don't know. If the lines don't appear, I can't tell. Anyway, so it's a vacuum in there, right? There's nothing. So can the heat conduct? No, because there's nothing for it to pass through to get to the Earth. Can it convect? Again, there's nothing for it to move with to get to the Earth. Okay? So how does the heat get from the sun? Here's all my heat. How does it get from the sun to the Earth? Well, in the form of radiation, in the form of light, right? That's how heat gets from the sun to the Earth, is it travels in the form of radiation or as light, right? This is the easiest example of this. And if you think about this, right, anything with a temperature, you and I have temperatures, we emit infrared radiation, okay? So for me, one of the easiest examples of this is like, let's say you put some bread in the toaster, and you push the little thing down, and the toaster starts to heat up. And if it's a cold morning, I don't know if you've ever like put your hands like not on the toaster, but like next to the toaster to feel the warmth. Okay, I mean, a lot of that is the infrared radiation coming off of the toaster, and that's what you're feeling, right? It's heat traveling in the form of light. So one way to kind of like package all of this together. So some applications. Okay, let's go back to our campfire. Okay, so here's the wood, and then I've got the fire. Okay, and if we're thinking about how this works, okay, if I want heat to conduct to me from the fire, I can put a metal rod in there. Kind of dumb, but you could do that, right? That would be conduction. Okay, if I wanted the heat to radiate to me, well, I could just come over here and put my hands over here, and radiation, heat in the form of infrared radiation is going to come off the fire and warm my hands. If I wanted to take advantage of convection, right, we could hang a pot up here and heat, right, all of this, the air that's in between the flames and the pot, that air is getting hot, and as it heats, it rises, and it's going to carry the heat of the fire with it to the pot, and it'll get hot, right? And there's also radiation coming up this way too. Um, uh, but so for example, with a campfire, you can see all of these, right? You can identify conduction, you can identify convection, and you can identify radiation when you're dealing with like a campfire or something like that. Some of the other applications of this stuff is if you think about, so for example, water bottles. I don't know if you own any of those water bottles where there's like one plastic sleeve and then inside of it you can see another one. And so there's this like empty space here, and then your beverage, your beverage goes in here, okay? And anyways, so why make water bottles like this? Why make water bottles with this gap in here? Okay, number one, right? If you think about what they're trying to block, the gap in there is going to block conduction, right? So if I have, right, if it's really hot out here and I want my drink to be really cold, can the heat directly conduct into my beverage? And the answer is that it can't, right? The heat can conduct into the wall of this thing, but then there's this space, right? And there's something in the space, right? It may be air. Some water bottles, they put like a really, really heavy gas in there, like argon or something. Because it's a really poor, it doesn't conduct thermal radiation, thermal conductivity. It has a really low thermal conductivity constant. Anyways, but that's the reason why they're doing this, is they're trying to block conduction, right? They have this gap in here, so the heat can't just conduct through the plastic and get into my drink. There's this space that's preventing it from getting into my drink. And then the same reason, right? So if there's something hot down here, can that heat convect into my drink, right? So if it heats the plastic, can this plastic convect up? No, it can't, right? It's solid. The plastic is not going to convect. Now there may be a really heavy gas in here, like I mentioned. There may be some argon in there that may heat, and then you might get little teeny convection currents of argon inside of there. But argon's a really big and heavy gas. If you wanted there to be nothing, right? If it was a vacuum in there, then there'd be no convection either. To get heat into my beverage, okay? So what's the only way that heat can get in? Well, it's radiation, right? So if you've made this from a clear plastic, light can get in there. Now, most plastics and glass actually block and reflect infrared radiation, but visible light can still get in. And the visible light can be absorbed by the material, and then the material will heat. But visible light still can get in there and heat the drink. So one way to get around that is, instead of making it out of plastic, you'll notice that a lot of them are made out of metal, but they still have that gap. So the metal ones are blocking most forms of radiation. They're blocking direct conduction, and they're also blocking direct convection, right? That's why water bottles are made this way. And if you think about it, double pane glass windows are the same way, except for, you don't want to make a window out of a sheet of metal because you do want to see out of it. So the window ones are not as effective at blocking heat radiation in the form of light, although glass does reflect most infrared radiation, which is kind of nice. But anyways, so here's a quick tutorial on all of this stuff. Let us know if you have any questions about heat transfer, and good luck preparing for the final. Thanks, everybody. Bye.